we are going to go over the answers to the first page on sheet F, which has some practice questions. The first couple of questions are for some spring mass oscillators, which we've gone through some problems a couple of times. So I've just got the answers up here. So take a second to check over your answers. If there's anything that doesn't match or if you're unsure of, make sure you write that down, post a comment in the Teams app, and we'll make sure that we get to that question. But after this, we're going to go over specifically the different problems in the next part, which is the pendulum, because I wanted to make sure we went over one of those pendulum problems completely. So pause the video, make sure you check over your answers for these problems, and then we'll get into the next question. Okay, so let's go over that pendulum problem. So a bunch of information is given to us right at the start. The only thing that we'll try to make mention of is this delta H depends on how far you pull the angle back, as does this arc length S. I essentially just solved those values for you because that's not what we're interested in right now. But if you do want to try and check to see that these values match up to the length and the angle, go ahead and do that. But let's start with an FBD for the pendulum bob when it's pulled up to its maximum positive amplitude. So we've actually got a couple of forces going on here. We've got our force of gravity and got our force of tension. Now we're definitely going to come back and reference this FBD a little bit later, so let's keep that handy. For period and frequency, that part should not be too bad. We have an equation for the period of a pendulum. So we've got our length, that's 0.253 meters. G, I use 10 newtons per kilogram. You can use 9.8, whichever one you like. And I got a value for the period of about 1 second. And since frequency is 1 over period, frequency is 1 hertz. Okay, so the next part of the question wants to know when the pendulum reaches its equilibrium position, how fast is it going? So we're going to use conservation of energy here, similar to what we've been doing with our spring mass oscillators. We know that our maximum kinetic energy is going to happen at the equilibrium position, and that must be equal to the maximum potential energy, gravitational potential energy here, and that's going to happen up at the highest point. So we've got 1/2 mv max. So that v max is the velocity it has when it's here. That must be equal to mgh. We're going to set potential energy equal to 0 here. So whatever potential energy has there, it's the amount above 0. So again, at this point now we can cancel out our m, make things a little bit easier. We'll use 10 newtons per kilogram for G, and our H is 0.0038 meters. That's that height above where it is. And this is where it's a little bit different than the spring mass oscillator. In a spring mass oscillator, that maximum position is that X value, which is however far compressed that spring is. But notice how here in our energy, this delta H has to do with this change in height, which is related to this arc length, but not equal to. So just make sure you watch out for that. So putting in those values there, I get a maximum speed of 0.28 meters per second. In trying to write our position function, so for the amplitude here has to do with the path length, that arc length from here to here. So that part was given to us in the problem, and it said that the bob is going to start at the maximum positive amplitude. So that's going to give us 0.044 meters cosine 2 pi. Our frequency is just 1 hertz, and we've got our t. So there's our position function. Now we want to figure out what's the maximum force experienced by the bob from the force that's causing the simple harmonic motion. This is where it gets a little bit more complicated than the spring mass oscillators. We have to isolate which aspect of those forces are causing the simple harmonic motion. To do that, we're going to draw some details onto this FBD that we've got here. So I'm going to add this dotted line here so we know that that angle is our angle theta. And if I extend a line here, we should also see that this angle must be theta. And I can break this force into components. There is a force in this direction that is Fg cosine theta. Let's make it a dotted line here because it's a component of this. And then there's a component that is this way, and that is Fg sine theta. Remember that simple harmonic motion comes as a result of a Hooke's law force, a force that brings the object back towards the equilibrium position. And in this diagram, that's going to be this. Fg sine theta is the force that is pulling the pendulum bob back towards equilibrium. And what you can try to conceptualize is as this angle decreases, the amount of force tangential to that path is going to get smaller and smaller, and then by the time that the pendulum bob reaches equilibrium, now there's no Fg in this direction. And hopefully you can see the parallels between that and a spring force. The spring force reaches 0 when the mass gets to the spring's equilibrium position. Here, the component of gravity that's tangent to the path reaches 0 at this point. We're not going to focus on these other forces for right now. We don't really need to answer these questions, but this is the force that we're going to analyze. That's the force that's causing the simple harmonic motion. We want to know where is that force going to be maximum and what would that value be. So that maximum is going to happen at our largest angle. So that maximum force is going to be mg sine theta. Our mass is 1 kilogram, 10 newtons per kilogram for g, and sine of 10 degrees. So all that is going to work out to be about 1.7 newtons. And then since acceleration is going to be max force over mass, our mass is just 1 kilogram, so our maximum acceleration is just going to be 1.7 meters per second squared. And lastly, we're going to look at our graphs. We're going to do the same approach that we do for the spring mass oscillator. We want to think about where is this graph going to start at t equals 0, and where is it going to go after that, looking at some key points. If we start at the maximum positive amplitude, I've put a frame of reference here for us to use to help us. At that point, we're at our maximum positive position, and that means the force is in that direction. So at the beginning, our force is a maximum value, and it's negative. And then by the time the pendulum bob reaches equilibrium, that force is at 0, swinging back up to the other side, where now that force will be pulling it in the positive direction. And by now you should be able to think about where the graph goes from there. Same as always, the acceleration graph looks the same shape as the force graph. For velocity, if we release from rest, our initial velocity is 0. If it's going to be swinging this way, it's going to be the fastest at equilibrium, and notice how it's now going in the negative direction. And then it slows to a rest up here. And we can kind of see where it goes from there. For position, I'm using S here for the arc length. It's the position along that path. Our maximum position in the positive direction is where we start. So we start up here. We go down to equilibrium, and then all the way up to our maximum positive position and back. And lastly, we'll look at our energy graphs. So we'll start with kinetic energy. At the release point, we have 0 kinetic energy. As we swing through the equilibrium position, that's where we have our maximum value. We swing up to the other side where we come to rest again. As we swing back through equilibrium, we have our maximum value again, and we come back to rest from where we started. So remember, this is showing just one oscillation. We know that the gravitational potential energy must just look like the inverse of this, where we have 0 kinetic energy, that's where we have our maximum potential. Where we have maximum kinetic energy, that's where we have our minimum potential, and so on. And there we have our graphs.